Hi, everybody. The first talk of this morning is the speaker is Raymond Yeung from the Chinese University of Hong Kong. The title is a geometrical interpretation of universality quantified in equality and its applications to different branches of mathematics. Let's welcome.
Okay, thank you very much, Professor Ding. My name is Raymond Yeung from the Chinese University of Hong Kong. I would like to thank the organizers for inviting me to give this lecture. Well, I'm very happy to be able to give the physical lecture this morning due to the bad weather. Okay, so in this lecture, I'm going to talk about some work that I did some 20 years ago, which was about the study of entropy inequalities, which led to very fruitful results in fields related to the Shannon entropy. Recently, I realized that this framework can actually be applied to virtually any so-called universally quantified inequalities, and therefore, I would like to share this idea here. So in this lecture, I'm going to first say a few words about inequalities and universally quantified inequalities. And I'm going to give a quick review of the results that we have obtained in information theory so far. And then I'll apply the same geometrical interpretation to some inequalities I'm familiar with, including the Markov inequality in probability theory, and also the Cauchy-Scharwz inequality for the inner product space. Okay, so we are very familiar with this. We consider in the Euclidean space Rn, and we consider function fx. And then we consider the inequality fx greater than or equal to 0. So we can actually identify this inequality with a region in the Euclidean space, namely that all the set of all vectors x in Rn such that fx is greater than or equal to 0. So if f is quote-unquote continuous, then by setting the inequality to equality, we can get the boundary of the region. So the picture looks something like this. So we have the curve fx equals to 0 being the boundary. On the one side, we have fx greater than 0, and on the other side, we have fx less than 0. Okay, so what are universally quantified inequalities? Actually, we all know what they are, except possibly the terminology from mathematical logic. So here are some examples. For all x in R, the quadratic x squared plus x squared minus 2x plus 3 is greater than or equal to 0. So basically, a universally quantified inequality is such that if x satisfies a certain condition, for all x satisfying a certain condition, then a certain inequality holds. And in probability theory, we have the Markov inequality, which says that for any non-negative random variable t, for any fixed constant a greater than 0, the probability that t greater than or equal to 0 is upper bounded by the expectation of t divided by a. And the Cauchy-Scharwz inequality says something for the inner product space. We let E be a real inner product space. For the purpose of this talk, I'm going to stick with a real inner product space, and that's good enough for illustrating the concepts. For any vectors u and v in the vector space, in the inner product space, we have the inner product of uv squared less than or equal to the inner product of u and the inner product of v and v. And in information theory, we have the well-known independence bound for the Shannon entropy, namely that for any discrete random variables x1 and x2, the entropy of x1 plus entropy of x2 is greater than or equal to entropy of x1 comma x2. Okay, the question is there a geometrical interpretation of such inequalities? Okay, so now we talk about some known results in information theory. So first of all, for those of you who are not familiar with Shannon's information measures, they are defined as such. For discrete random variable x, the Shannon entropy is defined as h of x equals minus px log px summing over all the x. And for two random variables x and y, the joint entropy is defined as minus summation pxy log pxy summing over all x and y. Okay, so now we can extend this to any number of random variables. So now suppose we fix the number of random variables to n, and for a random vector x1 up to xn, there are 2 to the power n minus 1 joint entropies. Namely, that for n equals 3, there are 7 joint entropies. The entropy of the single variables, the entropy of the pair of variables, and entropy of the 3 random variables together. Now, for each of these random vectors consists of n random variables, we can compute the 2 to the power n minus 1 joint entropies. And we regard this as a vector in the r to the power 2 to the power n minus 1 Euclidean space. Okay, so in 1997, I came up with this geometrical framework. So as I said, you have n random variables, and you compute the entropy vector, and which is regarded as a point in the 2 to the power n minus 1 dimensional Euclidean space. So you plot a point in the Euclidean space with the axis here being the with the axis here being the joint entropy of the subsets of random variables. Okay, so what we do is that you can exhaust all possible joint distribution for the n random variables to form this region. So what you do is that you keep calculating the different entropy vectors, and then you eventually take the union, and it becomes a region which we call gamma n star. Okay, so formally, gamma n star is all the vectors in this Euclidean space such that the vector corresponds to the entropy vector of some joint distributions. Okay, now the interesting thing is that this region gamma n star is not even closed. Okay, however, if you take the closure, it turns out to be a convex cone. That's why I illustrated it in this way, in this form. And as I'm going to show, this region gamma n star is very fundamental because it characterizes all entropy inequalities involving n random variables. Okay, so let's consider an inequality, let's say a linear one of the form B transpose H greater than or equal to 0, and we want to see whether it always holds or not. Now, this is the situation that it always holds. So this is the region gamma n star. If the half space induced by B transpose H greater than or equal to 0 completely contains the region gamma n star, then whatever entropy vector you come up with, it will be inside the region gamma n star, which in turn is completely contained in B transpose H greater than or equal to 0, and that's why it is on the right side of the inequality, and therefore this inequality, we say that the inequality always holds. Now, on the other hand, if the half space induced by B transpose H greater than or equal to 0 cuts into gamma n star, then we can come up with an entropy vector which is on the wrong side of the inequality. So that's why we say that the B transpose H greater than or equal to 0 does not always hold. Okay, there is an associated region called gamma n star, gamma n. Now, we are going to use the notation x alpha to denote the collection of random variables xi, I, and alpha. It is well known that for any n random variables, the following polymetroid axioms are satisfied. Namely that in non-negativity, all entropies are non-negative, non-decreasing, namely that h of x alpha is less than or equal to h of x beta if alpha is a subset of beta. And the submodular inequality, which says that h of x alpha plus h of x beta is greater than or equal to h of x alpha union beta plus h of alpha intersect beta. Okay, and we let gamma n be the intersection of all these inequalities, because you think of each inequality being a half space in the Euclidean space, and you take the intersection of all these half spaces. And because they are all satisfied by all the all the joint distributions, we immediately see that the gamma n actually gives an outer bound on gamma n star. The question is whether the two regions coincide or not. Okay, next I'm going to introduce a type of inequalities called Shannon-type inequalities. Basically, these are inequalities that are implied by the polymetroidal axioms. Now, the situation is like this. Suppose this gamma n star, and the outer bound is gamma n, and we have a inequality B transpose H greater than or equal to 0 that completely contains gamma n. In that case, for any entropy vector that you can ever come up with, it lies inside gamma n star, which in turn is inside gamma n, and in turn satisfy the inequality B transpose H greater than or equal to 0. So, and we call such an inequality a Shannon-type inequality, which is implied by the polymetroidal inequalities, and it holds for all joint distributions. Okay, in 1998, rather surprisingly, with my collaborator Zhen Zhang, we discovered a so-called non-Shannon-type inequality for 4 random variables. So the situation is like this. So this gamma 4 star, and the outer bound is gamma 4. This inequality, which is usually referred to as ZY98, okay, cuts through the gap between gamma 4 and gamma 4 star, and this clearly shows that gamma 4 star, even if you take a closure, is strictly smaller than gamma 4, and so this implies that Shannon-type inequalities are incomplete. Okay. Now, subsequently, other non-Shannon-type inequalities were discovered. First by a group of mathematicians from UCSD and other places. They actually used a supercomputer to help discover new non-Shannon-type inequalities, and they were able to do so for like 6 or 7 of them. And then subsequently, Matouche, a Czech mathematician, were able to prove analytically that for 4 random variables, there actually exists an infinite number of non-Shannon-type inequalities. And not only that, the region gamma 4 star, even after taking a closure, is not even a polyhedral cone. Okay, there's a curvature on this region. Okay, if you're interested in this topic, and I would refer you to a very nice blog by Terence Tao entitled "Special Cases of Shannon Entropy." Okay, now it turns out that this the study of this entropy region, gamma star, is closely related to many other subjects. On the right-hand side, we have network coding, Kolmogorov complexity. There's a special structure of combinatorics, and also finite group theory. There's actually one-to-one correspondence with these subjects with entropy. And on the left-hand side, the study of entropy inequalities actually have implications on them. These include probability theory, quantum mechanics, cryptography, matrix theory, and matroid theory. In the interest of time, I'm not going to go through all of these, but I would like to give you a flavor of what these things look like. Okay, if you're interested in this subject, I will refer you to my expository paper that appeared in Communications and Information Systems back in 2015 with the title Facets of Entropy. Okay, so the correspondence with Kolmogorov complexity was discovered by some mathematicians from the Kolmogorov school. Okay, so the one-to-one correspondence goes like this. Suppose now we know that for the entropy, the inequality on the top actually holds for all joint distribution for x1 and x2. Okay, entropy of x1 plus entropy of x2 is greater than or equal to entropy of x1 comma x2. Now, the corresponding inequality for Kolmogorov complexity is the following. For x, you replace this by k, which stands for Kolmogorov complexity. The random variable x1, you replace this by a sequence. Okay, this stands for the Kolmogorov complexity of the sequence x1. You do the same thing for the random variable x2. And for on the right-hand side, x1 comma x2, the random variable, you write this as small x1 comma x2, which is the joint Kolmogorov complexity of the two sequences. Okay, So it turns out that if an inequality, such an inequality holds for entropy, then the corresponding inequality also holds for Kolmogorov complexity and vice versa. Okay, so with this, you start with a non-Shannon-type inequality for the Shannon entropy, then you can immediately translate into what I call a non-Shannon-type Kolmogorov complexity inequality. Now, another example is about finite groups. Okay, this was the work done by my former student, Terence Chan, in 1999. So the setup is the following. So we let G be a finite group and G1, G2 up to Gn be subgroups. And we use the notation G sub alpha equals the intersection of Gi, I in alpha, which also turns out to be a subgroup. And turns out there's a one-to-one correspondence between entropy inequalities and group inequalities in the following way. Again, we start with this well-known inequality for Shannon entropy. So for H, you replace this by a log, and you have a fraction. Upstairs, you have the order of G. And for the inequality up there, you have the random variable x1. Here, downstairs, you write the order of G1. And you do the same thing for the second term. And for the right-hand side, the joint entropy of x1 and x2 becomes the log. And upstairs, you also have order of G1. And downstairs, here's x1, comma x2. And so the corresponding term here is the order of G1 intersect G2. Okay. It turns out that if such an inequality holds for entropy, always holds for entropy, the inequality at the bottom always holds for any group and finite subgroups G1 and G2, and vice versa. Not only for this particular example, but for any inequality, for Shannon entropy, for any inequality of this form for groups and subgroups. And again, non-Shannon type group inequalities can be obtained accordingly. You just start with the non-Shannon type inequality for entropy, and then you can obtain a group inequality accordingly. And if you start with Z198, then you obtain something like this, okay, which looks pretty complicated, and nobody seems to be able to know what it really means. Now, one thing I would like to point out is that this inequality, although it holds for any group and finite subgroups G1 up to G4, so far no direct group theoretic proofs of this inequality exist. Okay, so I think this is a very important problem to work on. If we find a direct group theoretic proof of this inequality, then it will shed light on its meaning in group theory. Okay, for matrix theory, it has something to do with positive definite matrices. Okay, so we let H define the differential entropy of a collection of continuous random variables. Okay, by substituting the differential entropies of a Gaussian vector with covariance matrix K, which can be any positive definite matrix. Now, from, for example, this inequality, which is well known for the differential entropy, the joint differential entropy of x1 up to xn is less than or equal to the sum of the differential entropy of the individual random variables. One can obtain the Hadamard inequality like this. Okay. Now, this is not something new. It dates back to at least to Bellman. Okay. This technique is known for a long time. Now, now with the discovery of non-Shannon-type inequalities, I'm not going to get into details. For the original non-Shannon-type inequality, it was discovered for discrete entropies, but it also turns out to hold for differential entropy. I'm not going to get into that. But starting with non-Shannon-type inequalities for the Shannon entropy, one can obtain inequalities for positive definite matrices like this. For example, from Z198, the corresponding inequality is like this, where K sub alpha denotes a principal minor of a 4x4 positive definite matrix K. Okay, so this holds for any 4x4 positive definite matrix K. So again, I mean the meaning of such inequalities are yet to be understood. Okay, now for 3x3 positive definite matrices, in the back about 10 years ago, we showed that there actually exists no inequalities on the principal minors beyond the polymetroid axioms. But 4 by 4 is not the case. Okay, so there are also some implications in matroid theory, because matroid theory is also closely related to entropy. But I'm not, in the interest of time, I'm not going to skip. I'm not going to go through this. If you're interested, you can refer to the slides that I have posted. Okay, now I'm going to switch gear to some observations that I made very recently. So I recently realized that this framework can be equally applied to other inequalities in other fields. Okay, these fields are not entropy related at all. Okay. So first, I'm going to talk about an example in probability theory, which is very well known. Now, the Markov inequality says that for any non-negative random variable t, for any a greater than 0, strictly greater than 0, the probability that t is greater than or equal to a is less than or equal to the expectation of t divided by a. Now, here we treat a as a constant. Or we can write this as expectation of t is greater than or equal to a times probability of t greater than or equal to a. Now, here the interpretation is the following. Now, expectation of t and probability that t is greater than or equal to a are two quantities we are interested in. And in particular, we're interested in the relation between these two quantities. Okay. Now, please pay attention to the color code, the blue and the red. Now, so let me just reproduce this. Okay, this is the Markov inequality. So I'm going to define, like in the spirit of what we did for the Shannon entropy, we're going to define the achievable region with it's a two-dimensional achievable region with the axis denoted by P and M. Now, please pay attention to the color code. This is red and this is red. Okay, so P corresponds to the probability that t is greater than or equal to a, and M, which is in blue, corresponds to the expectation of t. Okay, we're going to define the region psi a. A is a given constant. Okay, psi a of a star is equal to the set of all pairs Pm, such that Pm is equal to P is equal to the probability of t greater than or equal to a, and M is equal to the expectation of t for some positive non-negative random variable t. Okay. Now, since P being corresponds to a probability is between 0 and 1, we define the outer bound induced by the Markov inequality as follows. Okay. Psi of A is equal to Pm such that P is between 0 and 1. And M greater than or equal to AP. M greater than or equal to AP corresponds to expectation of T greater than or equal to A times probability of T greater than or equal to A. Okay. Okay, now question is psi A star equal to psi A? Okay, this is what it looks like. This is the x direction is P, the y direction is M. Okay, this M equals AP. Okay, and M greater than or equal to AP corresponds to everything above this this line, and this is the strip corresponds to constraining P to between 0 and 1. And this is the outbound psi A. Okay. Now, the question is whether in this region, every point is achievable by some non-negative random variable t. Now, if not, there may exist constraints on P, the pair P and M beyond the Markov inequality. So let's see how things go. It turns out that psi A is achievable everywhere except on the boundary. So this is the point 1, comma P, okay, and everything on this line which is above this point, including the point itself, are not achievable, okay, and everything else in the region is achievable. So the Markov we can say that the Markov inequality almost completely characterizes the relation between the probability that T is greater than or equal to A and the expectation of T, okay. Okay, the second example that I would like to consider is the inner product space. Okay, here's a setup of the Cauchy-Scharwz inequality. So we let V be a real inner product space. Now, for this discussion is it suffices to consider inner product, real inner product space. I don't want to get into the complex inner product space, which makes things more complicated, but doesn't quite extend the notions. Now, for any vectors u and v, we have the inner product of uv squared less than or equal to the inner product of u and u, and the inner product of v and v. Okay, here the three quantities of interest are the inner product of u and u, the inner product of v and v, and the inner product of u and v. And we want to find out we are interested in the relations between these three quantities. So we define the achievable region accordingly. Now this time the region is a subset in the three-dimensional Euclidean space. So this is the set of all triples x, y, z such that x is equal to inner product of u and u, y is equal to the inner product of v and v, and z is equal to the inner product of u and v for some vectors u and v in the inner product space. Okay, now since the inner product of u and u and the inner product of v and v are always non-negative, we define the outer bound induced by the Cauchy-Scharwz inequality as psi xyz such that xy is greater than or equal to 0. So please pay attention to the color code. Okay, xy corresponds to uu and vv, the inner products. Okay, they're always non-negative due to the setup. And also the Cauchy-Scharwz inequality z squared less than or equal to xy. So it corresponds to this inequality here. Okay. So again, the question is whether phi star is equal to phi. Okay, so this is what it looks like. This is the x, y, z directions. We are looking into the origin from this direction, and so this is the shape of z squared equals xy. Okay, this is a shell, and z squared less than or equal to xy is actually like a bullet, pointing to the origin from this direction. So this is psi, and this is phi. Okay, so the first, there's a theorem which is a very elementary one, is the following. Now, for an inner product space V, phi star is equal to phi if dimension of V is at least equal to 2. If dimension V is equal to 0, then the phi star is just the origin. If dimension is equal to 1, then phi star is all the triples x, y, z such that x, y is greater than or equal to 0. And z squared is equal to xy. It's not less than or equal to. Okay? Now the proof. Okay, I think the case for dimension v equals 0 and dimension v equals 1 are straightforward. Okay, very trivial. What really needs a proof is the case for dimension v is greater than or equal to 2, and it actually hinges on this proposition, which says that if dimension v is at least equal to 2, then for any non-zero vector u in v, there exists a unit vector w such that it is orthogonal to u. Okay, now so the situation is like this. It's also very intuitive. This is any vector u, you can find a vector w which is orthogonal to it. Basically, that is what it is. Now, so I proved this proposition from scratch. And it turns, I would like to remark that the proof of proposition 1 actually invokes every axiom of a real inner product space, namely that uv is equal to vu, linearity au plus v, comma w is equal to a times the inner product of uw plus b times the inner product of vw, and inner product of u and u is strictly greater than 0 if u is not the 0 vector. So things are very tight, right? So the remarks are the following. If dimension v is equal to 1, then phi star is the boundary of phi, and precisely phi star is not equal to phi precisely because for if the dimension of v is equal to 1 for a vector, you cannot find another vector which is orthogonal to it. Okay? And so in this case, phi star is just the boundary of phi, namely that you set the inequality to equality. And the Cauchy-Scharwz inequality does not completely characterize the relation between UU, VV, and UV when dimension v is equal to 0 and 1. Nevertheless, there exists no inequality on UU and VB and UB that holds for all inner product space regardless of the dimension of V, okay, which is not implied by Cauchy-Scharwz inequality. So in this sense, the Cauchy-Scharwz inequality is almost good enough, okay, for characterizing all the relations between UU, VB, and UB. Okay. Okay. So this is the situation. This region is phi. Okay. When the dimension V is equal to 0, it is just the origin. When dimension V is equal to 1, the achievable region is equal to the boundary of phi. When the dimension V is at least equal to 2, then the whole region is achievable. Okay, so here's the conclusion. We propose a geometrical interpretation that captures the very meaning of a universally quantified inequality. And specifically, a universally quantified inequality is an outer bound on the achievable region. So the new idea here is to consider the achievable region. And the ultimate problem is to completely characterize the achievable region. Now, in information theory, this approach has led to very fruitful results, in particular the discovery of non-Shannon-type inequalities. And also it has led to very fruitful results in a number of subjects related to the Shannon entropy. In this talk, we have applied this approach to the Markov inequality and the Cauchy-Scharwz inequality. Now, the results are not really surprising, but they help clarify the issues. And I advocate that we can apply this, this geometrical interpretation to other branches of mathematics, to any universally quantified inequalities, and this may lead to the discovery of new fundamental inequalities, fundamental constraints, in particular inequalities on quantities of interest. Here, I want to emphasize that this is fundamental constraints. These constraints are not necessarily in the form of inequalities. For example, the achievable region may not even be closed. Okay, so sometimes they can be very weird. The achievable region can be very weird, as in the case of the achievable region for the entropy vectors. Okay, I'm working on a manuscript on this. Hopefully, by the end of summer, I would be able to finish this. Okay. All right. Okay. I encourage you to apply this to your favorite inequalities that you're familiar with. Have a dip. Thank you.
Okay. Any question?
Can you say a bit more about the nature of ZY98, or like how you found it, or what it is?
Okay. So I can tell you a little bit about how it can be proved. It is a pretty mysterious thing, which I owe my collaborator a lot for the discovery of this inequality. So let me. Okay, I'll try to do it here. Okay, so suppose you have 4 random variables x, y, and z and t to start with. Okay, and what you do is you create two I would say call them auxiliary random variables. Okay, x prime, y prime. Okay, so you can think of it like this. So this is a Markov chain. Conceptually, you can think of it as you start with zt, you pass it through a channel or a conditional distribution to obtain xy. Okay, and then you pass it through the same channel but independently to obtain another copy of x prime, y prime. Okay, now this technique is now called the copy lemma in the literature. Okay, Now this Markov chain can be constructed for any any joint distribution for 4 random variables. Okay. Now you have 6 random variables, and then you apply the polymetroidal axioms or polymetroidal inequalities for 6 random variables. Okay. Then after a while, miraculously, the 2 auxiliary random variables x prime, y prime disappear. Okay, because you keep applying some of these inequalities, and after a while, the auxiliary random variables x prime, y prime disappear, and you end up having an inequality for 4 random variables that holds for all distributions for 4 random variables, but it's not implied by the polymetroidal axioms for 4 random variables. It's a very miraculous technique, and I would say very mysterious, because after more than a quarter of a century, this is still the only way that one can possibly discover and prove non-Shannon-type inequalities, and no one knows exactly why it works. Okay, and no one knows exactly why and when it would work. Yeah. So it's very mysterious. I would say that without the collaboration with Zheng, we probably are still in vain for searching for non-Shannon-type inequalities.
Any more questions?
Well, when P is bigger than equal to 1, there's a Banach space. Most of the things apply. What about P less than 1?
Well, I think we have to look into it case by case. And so my view is that by applying this view to different inequalities, there's a great potential that we can discover new fundamental constraints on quantities of interest. Yeah, each problem is very different. We have to look into it case by case.
More questions? Okay, let's thank the speaker again.
Okay, thank you very much.